Welcome, my friends, to Science, to Sleep By. As you settle in, your mind drift into the vast expanse of space. Tonight, I want to take you on a journey across unimaginable distances, through time, and into the limits of what we call possibility. Many of us have gazed up at the stars and wondered, will humanity one day travel beyond our Milky Way galaxy? It's a thought that feels both thrilling and terrifying. But the truth is, as awe-inspiring as the dream may be, there are profound scientific reasons why we may never escape the Milky Way. So let's slow down, breathe, and gently wander together through the mysteries of space, as I explain why the stars beyond our galaxy may forever remain out of reach. When we talk about why humanity may never leave the Milky Way, the very first and most obvious reason lies in the sheer size of our home galaxy. To understand this, it helps to step back and consider just what the Milky Way really is. From Earth, when you look up on a clear night far from the glare of city lights, you might see a hazy band stretching across the sky. That band is not a cloud, nor a trick of the atmosphere. It is the light of billions upon billions of distant stars, smeared together by their immense distance from us. That band is the Milky Way itself, seen from within. But what we see with our eyes barely scratches the surface of its true immensity. The Milky Way is a spiral galaxy, a sprawling city of stars, gas, dust, dark matter, and black holes, measuring roughly 100,000 light-years from one end to the other. A single light-year, remember, is the distance light travels in 1 year, moving at nearly 186,000 miles per second. Multiply that by 100,000. And you begin to understand the mind-bending scales involved. Even within our galaxy, moving from one star to another is an extraordinary challenge, and the thought of crossing its entire diameter becomes nearly unimaginable. To put that into perspective for a human audience, consider the fastest spacecraft ever built. The Parker Solar Probe, launched by NASA, is currently the fastest object humanity has ever made. It travels at a speed of about 430,000 miles per hour, a velocity so staggering that it could circle Earth in less than an hour. And yet, at that pace, it would take over 17,000 years just to travel a single light year. The nearest star beyond our Sun, Proxima Centauri, a little over 4 light-years away. That means even the closest step outside our solar system would require tens of thousands of years of travel with current technology. Now extend that to the scale of the Milky Way, which is 100,000 light-years wide. Suddenly, the prospect of leaving the galaxy does not just seem daunting. It begins to feel outright impossible. The immensity of the Milky Way is not only about its length and breadth, but also its depth and complexity. It contains somewhere between 100 billion and 400 billion stars, each potentially with its own planets, moons, and mysteries. To simply map and understand what lies within our own galaxy would take humanity longer than the entire span of recorded history. In fact, if you imagine visiting one new star system every single day, it would take you over 1 billion years to even begin to scratch the surface. This helps us recognize that leaving the Milky Way is not just about crossing a boundary. It is about abandoning a vast, nearly infinite frontier that is still largely unexplored. The analogy often used is to compare our galaxy to a great ocean. We are like tiny sailors in a canoe, barely skimming the shoreline of a continent-sized sea. We have not charted the waters, we have not discovered the hidden islands, and we have not even glimpsed the depths below. To think of crossing to another galaxy is to imagine skipping over the ocean entirely without ever really knowing what lies within it. That, in itself, raises a philosophical question. Why would we leave behind such immensity when our own home still has so much to reveal? But size also has a more practical consequence. If humanity were to attempt leaving the Milky Way, it would not be as simple as building a faster ship or designing more efficient propulsion systems. We would be dealing with distances that multiply every limitation we already face in space exploration. Even communication becomes a challenge. The signals we send, traveling at the speed of light, take minutes to reach planets within our solar system, and years to reach the nearest stars. To send a message across the width of the Milky Way would require 100,000 years just for the signal to arrive. Imagine a society attempting to coordinate across such timescales. Empires and nations rise and fall on Earth in mere centuries. And yet intergalactic communication would demand patience beyond any human institution or culture we can imagine. Another factor tied to the Milky Way's size is gravity. The galaxy is not simply a flat disk of stars floating aimlessly in space. It is bound together by an enormous gravitational well created by both visible matter and an even greater mass of dark matter. To escape the galaxy, humanity would need to overcome this gravitational binding energy, which is orders of magnitude beyond what we are capable of generating. It is similar to the way rockets on Earth must fight against the pull of our planet's gravity to reach orbit, except magnified to an almost incomprehensible scale. Escaping Earth requires energy. Escaping the solar system requires even more. But escaping the Milky Way would be like climbing a mountain so vast that its summit disappears into eternity. The scale of the galaxy also means that time itself becomes a limiting factor. Human lifespans are measured in decades, civilizations in centuries, and species survival in perhaps millions of years. Yet the timescales required to traverse the galaxy, and certainly to leave it, extend into tens of millions, hundreds of millions, and even billions of years. The Milky Way itself is already over 13 billion years old, nearly as old as the universe itself. Stars are born and die in its arms, planets form and crumble, and black holes feast at its core, all across timescales that dwarf the existence of humanity. When you begin to measure journeys not in days, months, or years, but in millions of years, it becomes clear that the size of the Milky Way imposes a practical boundary on our ambitions, and yet, there is something strangely comforting in this immensity. The very fact that the Milky Way is so large means that it offers a lifetime of wonder and mystery. Our home galaxy is not a cage, but a cosmos unto itself. It contains star nurseries where suns are being born in clouds of gas and dust, neutron stars that spin like cosmic lighthouses, and rogue planets drifting in the dark with no star to call home. It is filled with phenomena so strange and so beautiful that simply learning to understand them could occupy humanity for as long as we endure. In this sense, the size of the Milky Way is both a limitation and an opportunity. It may mean we will never truly leave it, but it also means that we will never run out of places to go, stories to tell, and discoveries to make. So, when we ask why humanity may never leave the Milky Way, the first answer is simple yet profound. The galaxy is just too big. Its sheer scale outpaces not only our technology, but our imagination, our patience, and perhaps even the limits of what it means to be human. The Milky Way is a home so vast that it might as well be the universe itself from our perspective. A place whose edges are unreachable, not because they are forbidden, but because they are simply too far away for us ever to cross in the time allotted to our species. If the sheer size of the Milky Way gives us our first glimpse into the impossible challenge of leaving it behind, then the second reason we may never escape its grasp is even more fundamental: the cosmic speed limit set by the universe itself. At the heart of modern physics lies Albert Einstein's theory of relativity, which tells us that nothing with mass can travel faster than the speed of light. Light moves at an astonishing 186,000 miles per second, crossing nearly 6 trillion miles in a single year. For human beings, used to measuring distances in miles or hours of travel, this number feels almost infinite. And yet, in the context of the universe, even light is painfully slow. The Milky Way stretches 100,000 light-years across, meaning it takes light 100,000 years to travel from one end of the galaxy to the other. That fact alone illustrates why the dream of leaving the galaxy quickly becomes less about engineering and more about the laws of physics themselves. Imagine, for a moment, that humanity builds a spacecraft capable of approaching the speed of light. This would already be a feat so extraordinary that it might take thousands of years of scientific progress to achieve. But even then, if a ship could move at 99.9% the speed of light, it would still take 100,000 years to cross the Milky Way from one side to the other. And remember, that is just to reach the edge of our galaxy, not to travel beyond it into the intergalactic void, where the distances between galaxies become millions of light years. The nearest large galaxy to ours, the Andromeda Galaxy, is over 2 million light years away. Even at the speed of light, it would take 2 million years to reach it, a span of time that makes all of human history seem like a blink. From the first sparks of civilization in Mesopotamia to the present day, has been less than 10,000 years. Multiply that by 200, and you begin to glimpse the time required for light alone to make the crossing. The reason nothing can exceed this speed is tied to the very structure of the universe. According to relativity, as an object accelerates closer to the speed of light, its mass effectively increases, and the energy required to keep pushing it faster grows without bound. To actually reach light speed would require infinite energy, something that no civilization, no matter how advanced, could ever achieve. This is not a matter of building better engines or finding new fuels. It is a fundamental law of the cosmos. The speed of light is not just fast, it is absolute. It is the boundary line written into the fabric of space and time itself, and it defines the possible. This limitation has deep consequences for how we think about intergalactic travel. Even if future generations create technologies that allow us to approach light speed, the journeys would still take longer than the lifetimes of stars, longer than the survival of civilizations, longer than the timescales on which species evolve and vanish. A ship launched with the goal of leaving the Milky Way might never arrive while humanity still exists. By the time it reached its destination, Earth could be gone, our sun could have burned out, and the very memory of our species might have dissolved into silence. The speed of light, in this sense, acts like a cage one made not of walls, but of time. It is tempting to imagine shortcuts, to wonder if wormholes or warp drives could bypass this limitation. Science fiction often gives us these ideas, and they stir our imagination. But wormholes, if they exist, are unstable and fleeting phenomena, requiring exotic forms of matter and energy to keep them open. A stable, traversable wormhole is still theoretical, a speculation that may never become reality. Warp drives, meanwhile, rely on concepts of bending or contracting space-time itself, creating a bubble that moves faster than light relative to outside observers. But to generate such a bubble, calculations suggest one would need more energy than is contained in the entire universe. These ideas are fascinating, and perhaps future discoveries will reveal loopholes in the cosmic code, but as we understand physics today, the speed of light remains an unbreakable barrier. For everyday life, this cosmic limit feels abstract, but its effects are woven into everything we see. Light from the sun takes about 8 minutes to reach Earth, which means we always see the sun not as it is now, but as it was 8 minutes ago. Light from Proxima Centauri, the nearest star, takes more than 4 years to reach us, so when we look at it, we are looking back in time by 4 years. Look deeper into the Milky Way, and the starlight we see may already be thousands of years old. In this way, the speed of light transforms the universe into a kind of time machine, showing us the past rather than the present. But it also serves as a cruel reminder that even communication across galactic distances becomes unworkable. If a civilization on the far side of the Milky Way were to send us a greeting today, it would not arrive for 100,000 years, and by then, humanity might no longer be here to listen. This cosmic barrier forces us to confront not just physics, but philosophy. What does it mean to be bound within a galaxy? What does it mean to live within limits so immense that they feel like infinity? For some, it is frustrating to think that the stars of other galaxies may forever remain out of reach, tantalizing but unattainable. For others, it is a reminder that our own galaxy is vast enough to hold more wonder than we can ever experience. The speed of light, then, is not only a limit, but also a gift. It slows us down, forces us to focus on the richness of the here and now, on the worlds within our grasp, rather than the unreachable lights beyond. And yet, The human spirit has always pushed against boundaries. We once thought crossing oceans was impossible, that reaching the skies was beyond us, that stepping onto the moon was fantasy. Each time, ingenuity carried us farther. But the speed of light is not like the barriers of the past. It is not a technological hurdle to be solved, but a fundamental property of reality itself. Unless the laws of physics are rewritten, unless some deep truth we do not yet grasp is uncovered, this barrier will stand forever. It is a horizon we cannot cross, a constant reminder that space is not just vast, it is limited by the very rules of existence. To never leave the Milky Way then, not simply a matter of size, but of speed. The cosmic speed limit ensures that the stars beyond our galaxy are not destinations, but distant fires to admire from afar. They remain part of the backdrop of our universe, shaping our sense of wonder, but reminding us always of the boundary between what we can dream and what we can do. When considering the reasons why humanity may never leave the Milky Way, one of the most overwhelming obstacles is energy. The sheer scale of what would be required to send a spacecraft across interstellar, and certainly intergalactic, distances is so immense that it almost defies imagination. To move even the smallest object across such vast stretches of space requires energy far beyond what human civilization has ever produced, and far beyond what we can even envision producing with our current understanding of physics and engineering. While the speed of light acts as a theoretical barrier to motion, energy demands are the practical wall we run into long before we ever get close to such speeds. Energy lies at the heart of everything we do in space. When we launch a rocket into orbit, it takes an enormous amount of fuel simply to escape Earth's gravity. Just leaving our planet requires that we overcome the gravitational binding energy of Earth, and to do that we burn vast quantities of propellant. For perspective, NASA's Saturn V rocket, which carried humans to the moon, consumed about 20 tons of fuel every second during launch, and that was only to reach the moon, which is less than 240,000 miles away. The challenge becomes exponentially greater when we talk about leaving the solar system, let alone traveling to another galaxy. Each step upward in scale multiplies the energy required until the numbers spiral into near infinity. One way scientists calculate these demands is through a framework called the Kardashev scale, which measures civilizations by the amount of energy they can harness. Humanity currently sits at around 0.7 on this scale. We are a Type I civilization in the making, meaning we are approaching the ability to harness all the energy available on our home planet. A Type II civilization would be able to capture all the energy of its star, perhaps through something like a Dyson sphere, an imagined megastructure surrounding a star, to collect its light. A Type III civilization would control the energy output of an entire galaxy. To leave the Milky Way, in any realistic sense, a civilization would need to operate at or near Type III. That is how extreme the requirements become. Humanity is still struggling to generate clean, renewable power on a planetary scale, so the idea of managing stellar or galactic energy levels is beyond our reach for the foreseeable future. Let us look more closely at what it would take to push a spacecraft to speeds that make intergalactic travel even remotely plausible. The faster you go, the more energy is required. To accelerate a modest spacecraft, say with a mass similar to a commercial jet, up to even 10% the speed of light would require more energy than the entire world produces in a year, multiplied many times over. To reach half the speed of light would require energy on the scale of converting entire planets into fuel. The mathematics of this are not subtle. They are brutal. Kinetic energy increases with the square of velocity, which means every incremental push toward higher speeds multiplies the energy demands enormously. At near-light speeds, the energy demands effectively approach infinity. Even futuristic propulsion concepts struggle to address this. Nuclear fusion propulsion, for example, offers far greater efficiency than chemical rockets, and it could in theory allow a spacecraft to reach a fraction of light speed. But fusion itself is not yet a mastered technology on Earth. Even for generating electricity, we have been chasing controlled fusion for decades without success. To build a fusion-based spacecraft would not only require solving this monumental challenge, but scaling it up to unprecedented levels. Antimatter propulsion is another idea often proposed. Antimatter, when it collides with matter, converts completely into energy, making it the most efficient fuel possible. But antimatter is extraordinarily difficult to produce. In Earth's best particle accelerators, we can only generate tiny amounts, and the cost of creating a single gram of antimatter is estimated at trillions of dollars. To power a starship with antimatter would require tons of the stuff, meaning we would need energy equivalent to the consumption of entire civilizations just to manufacture the fuel. Solar sails, another proposed method, would rely on the momentum of photons from stars or even powerful lasers pushing enormous, reflective sails through space. While elegant in concept, the energy required to sustain such a push over intergalactic distances becomes insurmountable. The sails would need to be kilometers wide, and the lasers to propel them would need to draw on the energy output of entire stars for centuries. These methods, while theoretically intriguing, only underscore the problem. No matter how creative we get with propulsion systems, the energy required to leave the Milky Way simply dwarfs what humanity can produce. Energy is not just about propulsion, either. Consider the energy required to sustain life on such a journey. A spacecraft designed to travel across galaxies would need to function for millions of years, perhaps longer. It would need to recycle air, water, and food indefinitely. It would need to shield its passengers from radiation, provide artificial gravity, and maintain a functioning biosphere. The energy demands of simply keeping a crew alive, multiplied over generations or even eons, would add yet another layer to the already overwhelming requirements. And if the ship were unmanned, carrying probes or machines instead of humans, those machines would still need to operate flawlessly for unimaginable stretches of time, powered by sources that do not decay or fail. The scale of these challenges forces us to consider energy not as a resource we can merely accumulate, but as a fundamental constraint. Our civilization consumes vast amounts of energy every year, and yet even all of Earth's annual energy production would barely nudge a starship toward the speeds necessary to cross interstellar space. To attempt intergalactic travel, we would need to think on scales far beyond planetary or even stellar resources. We would need to capture and direct energy on galactic levels, harnessing power that dwarfs the sun itself. It is not that such ideas are uninteresting, they spark the imagination, but they belong to a realm of speculation so distant from our reality that they might as well be science fiction. In fact, even if we look at the possibility of using natural cosmic energy sources, the story does not get easier. Some have proposed using the rotational energy of black holes, tapping into the immense power generated at their event horizons. Others imagine harnessing the output of entire quasars, the blazing hearts of active galaxies. These ideas are breathtaking, but the engineering challenges are overwhelming. The energy is there, scattered throughout the universe, but capturing and controlling it requires technologies so advanced that they may forever remain theoretical. What the problem of energy ultimately reveals is that leaving the Milky Way is not simply a matter of distance. It is a matter of confronting the most fundamental limitations of physics, engineering, and resource management. We are bound not just by the speed of light, but by the colossal energy demands of moving mass across unimaginable distances. Even if we discover new propulsion methods, even if we solve fusion or antimatter production, the scale of what is required may always remain out of reach for a species like ours. It is not a lack of imagination that holds us back, but the cold arithmetic of energy, a truth written into the equations of motion and conservation that govern the cosmos when considering the reasons why humanity may never leave the Milky Way. One of the most daunting barriers we face is the question of energy. Every single movement in space, every acceleration, every attempt to push matter across the void, is paid for in energy. Here on Earth, we often take for granted what it takes to power a car, a city, or even an entire nation. But when we scale that up to the challenge of interstellar travel, let alone intergalactic travel, The energy demands explode into magnitudes so incomprehensible that they dwarf the sum total of all energy humanity has ever produced in its history. Energy is not just a technical hurdle in this context, it is a fundamental wall that stands in our way long before we even reach the cosmic speed limit. Take the example of rockets. To send a rocket into orbit requires staggering amounts of fuel just to escape Earth's gravitational pull. The Saturn V, the largest rocket ever successfully flown, guzzled 20 tons of fuel every single second during launch, all to move a relatively small payload into low Earth orbit. That effort only carried us a few hundred miles above the surface of our planet. Now consider the Moon, about 240,000 miles away. The Apollo program consumed vast reserves of fuel, time, and resources just to travel that modest distance compared to the size of the galaxy. The Milky Way is 100,000 light-years across, which is equivalent to 600 million trillion miles. When you compare that to a mere 250,000 miles to the Moon, the impossibility of scaling up becomes immediately clear. Scientists sometimes think about this problem in terms of the Kardashev scale, which ranks civilizations based on how much energy they can control. Humanity is currently below a Type I civilization, meaning we don't yet use all the energy that reaches Earth from the Sun. A Type II civilization would command the power of an entire star, perhaps with megastructures like Dyson spheres to capture every photon. A Type III civilization would harness the energy of an entire galaxy. To realistically contemplate leaving the Milky Way, a civilization would need to operate somewhere between Type II and Type III, managing power output on scales that are utterly beyond us. We are still struggling to provide clean energy for a single planet, while the scale required for galactic travel is so far removed from our reach it seems more myth than science. Let's consider numbers. If you wanted to accelerate a spacecraft the size of a modern airliner to just 10% of the speed of light, the energy needed would exceed the total global energy consumption of Earth for many, many years. To reach 50% of light speed, the energy requirement climbs so steeply it would mean converting entire planets into fuel. Kinetic energy increases with the square of velocity, which means every incremental increase in speed doubles and triples the demands, until they spiral toward infinity. By the time you get close to light speed, the amount of energy required exceeds all the energy available in the observable universe. Proposed propulsion technologies do not escape this trap. Fusion engines, which promise to unlock energy from the same process that powers the stars, remain an unrealized dream on Earth. Despite decades of effort, we have yet to produce a sustained, controlled fusion reaction that generates more power than it consumes. To expect that we could scale this up into a spacecraft powerful enough to push near light speeds is to leap far ahead of where science currently stands. Antimatter propulsion, in theory, offers perfect efficiency because matter and antimatter annihilate into pure energy. Yet antimatter is the most expensive substance we know how to create. The cost of producing a single gram runs into trillions of dollars, and a usable spacecraft would need tons of it. Even if we could create and store antimatter safely, the energy cost to manufacture it is astronomical. Solar sails, driven by photons from stars or by giant lasers, have been proposed as a way to sidestep the fuel problem. The concept is elegant. No need to carry propellant, only to capture the pressure of light itself. But the engineering required is breathtaking in scale. The sails would need to be tens or hundreds of kilometers across, and the lasers powerful enough to shine steadily for centuries. Even then, the acceleration would be agonizingly slow, and sustaining it over galactic distances would still demand energy output comparable to entire stars. And propulsion is only half the story. Energy is also needed to sustain life for such journeys. A ship designed to cross intergalactic space would need to maintain a closed ecosystem indefinitely. It would need to recycle air, water, and food flawlessly, shield its inhabitants from cosmic radiation, and maintain systems for millions of years. The energy to simply keep humans alive across generations of travelers would itself rival the requirements for propulsion. If the ship carried machines instead of people, they too would need power sources immune to decay, resistant to breakdown, and able to operate flawlessly for timescales that may spend millions of years. When we take stock of these requirements, the conclusion is sobering. Even if we invent better propulsion methods, even if we learn to master fusion, antimatter, or exotic energy sources, the sheer scale of what is needed to leave the Milky Way pushes us into the realm of Type 2 or Type 3 civilizations. That is not where we are, nor is it where we are likely to be anytime soon. The energy demands are not a problem of logistics or engineering, they are a problem of scale. Rooted in the laws of physics and the reality of resource limitations. It's true that nature provides immense sources of energy scattered throughout the cosmos. Black holes spin with rotational energy that rivals the output of millions of stars. Quasars blaze brighter than entire galaxies. Magnetars pulse with magnetic fields stronger than anything humans can imagine. But to tap these sources, to channel and control them, would require technologies so advanced that they exist only in the imagination. The energy is there, but the means to claim it is not, and may never be. This is why energy requirements stand as one of the most immovable barriers to intergalactic travel. They are not just difficult, they are overwhelming. To move beyond the Milky Way would mean capturing and directing power on cosmic scales, a feat so far beyond us that it reshapes the very way we think about possibility. When we look up into the night sky and see the countless stars stretched out above us, what we are really witnessing is a tapestry of cosmic history painted across billions of light years. Each point of light is not only a star, but also a message carried by photons that have been traveling for thousands or even millions of years to reach our eyes. This perspective alone reminds us how vast and isolated the universe truly is. But the challenge of leaving the Milky Way goes beyond distance, beyond energy, and beyond the speed of light itself. It connects to the deeper truth that the universe is not static. It is expanding. Space itself is stretching, and galaxies are drifting farther and farther apart. This expansion, first discovered by Edwin Hubble in the 1920s and later confirmed by generations of astronomers, creates a barrier so profound that it essentially ensures cosmic isolation for all galaxies, including our own. To understand the scale of this, it is important to remember that galaxies are not moving through space like ships sailing across an ocean. Instead, the fabric of space itself is expanding, carrying galaxies away from one another like raisins embedded in a rising loaf of bread. On smaller scales, like within the Milky Way, gravity overcomes this expansion and binds everything together. That is why stars orbit the galactic center, and planets orbit stars, and moons orbit planets. But on larger scales, between galaxies, this expansion becomes the dominant force. And the farther away a galaxy is, the faster it recedes from us. This relationship, described by Hubble's law, means that distant galaxies are rushing away so quickly that many of them are already beyond the reach of light speed travel. In fact, some galaxies are moving away from us faster than light itself, not because they are breaking the rules of physics, but because space itself is stretching between us and them. This reality creates a fundamental horizon. Astronomers call it the cosmic event horizon. Galaxies beyond this horizon are receding so quickly that no signal, no matter how fast, can ever reach them. Even if we could build a ship that traveled at the speed of light, it could never catch up. Those galaxies are already lost to us, forever disconnected from our cosmic neighborhood. As time moves forward, the expansion of the universe will push more and more galaxies beyond this horizon, until, billions of years from now, only the Milky Way and its closest companions will remain visible in the night sky. The universe will become lonelier and lonelier, with each galaxy locked into its own island of stars, cut off from the rest of the cosmos. For us, this means that the dream of leaving the Milky Way becomes not just improbable, but cosmically impossible. The expansion ensures that the vast majority of galaxies are permanently inaccessible. And the cruel irony is that the longer we wait, the more the universe takes away from us. Galaxies that are visible today will eventually fade beyond our reach, carried off by the relentless stretching of space. If we were ever to attempt leaving our galaxy, it would have to be soon on cosmological timescales. But for a species like ours, just learning how to explore our own solar system, the timeline of opportunity is already vanishingly short. This isolation also reframes the way we think about cosmic community. Many people wonder whether alien civilizations exist, and if so, why we have not yet found them. This is sometimes called the Fermi paradox, the apparent contradiction between the high probability of life existing elsewhere and the silence we observe. The expansion of the universe offers one possible explanation. Even if intelligent life thrives in distant galaxies, they may be so far away, receding so rapidly, that we will never detect their signals or meet them in person. The universe could be teeming with civilizations, but the walls of cosmic isolation prevent us from ever bridging the gap. Each galaxy becomes its own private cradle of life, isolated by physics itself. The expansion also connects deeply with the concept of dark energy, a mysterious force that drives the acceleration of the universe's growth. Discovered in the late 1990s through observations of distant supernova, dark energy makes up about 70% of the universe. It is invisible, elusive, and still poorly understood, but its effect is unmistakable. It is pushing galaxies away from each other at ever-increasing speeds. This acceleration means that cosmic isolation is not just a static fact, but a growing one. The future of the universe is one where galaxies become more and more isolated, where the night sky grows darker, and where the dream of intergalactic travel fades further into impossibility. Imagine, then, what it would mean to attempt leaving the Milky Way under these conditions. Even if humanity overcame every other barrier, energy, time, speed, we would still run up against the horizon created by expansion. The galaxies we might hope to reach are being pulled away faster than we could ever pursue them. It is like trying to swim across an ocean while the current carries your destination farther and farther away, faster than you can swim. No matter how strong you are, you will never arrive. This is the inescapable consequence of cosmic expansion. On a philosophical level, the isolation forced by expansion makes the Milky Way feel less like a cage and more like a final frontier. We are bound here, not because of failure or lack of imagination, but because the universe itself sets the terms of possibility. The Milky Way becomes our island, our continent, our entire world, not just because it is vast and rich in mysteries, but because it is the only part of the cosmos truly available to us. We can look outward and admire the beauty of other galaxies, but they remain as unreachable as dreams. The light from them is already ancient by the time it reaches us, carrying messages from the past that cannot be followed back to their source. Even within this sobering reality, there is a kind of beauty. The expansion of the universe ensures that the Milky Way is a self-contained cosmos, filled with hundreds of billions of stars and perhaps trillions of planets. We may never leave it, but we may also never need to. The wonders within our own galactic home are more than enough to occupy us for as long as our species endures. From the star-forming regions where new suns are born, to the black hole at the galactic center with its unfathomable gravitational pull, to the countless planetary systems waiting to be discovered, the Milky Way offers an inexhaustible supply of mysteries. Perhaps the expansion of the universe, by isolating us, is also guiding us inward to explore what is near, what is possible, what is within reach. But the inescapable truth remains: cosmic expansion enforces isolation. It is not just distance, not just energy, not just speed. It is the fact that the fabric of space itself is stretching faster than we can chase it. It is the ultimate wall between galaxies, the cosmic rule that ensures that each galactic home remains separate, like islands scattered across an infinite, ever-widening sea. For humanity, this means the dream of leaving the Milky Way is not only unlikely, it is sealed away by the very laws of the universe itself. If one imagines humanity someday building a ship capable of reaching the edge of the Milky Way, there is another reality waiting beyond that boundary, one often overlooked, but perhaps even more formidable than distance, speed, or energy. The intergalactic environment, the vast, empty, and hostile space between galaxies is unlike anything we experience even within the relatively calm cradle of our solar system. It is an environment that challenges not only the durability of machines, but also the very idea of sustaining life on such a journey. While space travel within the Milky Way is already perilous, venturing into the gulf between galaxies would mean exposing ourselves to conditions that are more extreme, more unforgiving, and more alien than almost anything else in nature. To begin with, intergalactic space is unimaginably empty. Within our galaxy, stars are separated by light years, but there is still structure, clouds of gas, dust, and dark matter, with occasional planetary systems and nebulae scattered in the darkness. Between galaxies, however, there is almost nothing. For millions of light years in every direction, a traveler would find no planets to land on, no resources to mine, no light to guide the way. It is an endless desert, where the concept of supply and refueling loses all meaning. Any spacecraft attempting to cross it would need to carry everything it requires from the very beginning: fuel, food, water, oxygen, and energy systems capable of lasting millions of years. In practical terms, this makes intergalactic travel nearly impossible. Even if we could find a way to move fast enough, the absence of resupply points would mean our journey is cut off from every form of support. But emptiness alone is not the only danger. Intergalactic space is also filled with high-energy radiation, cosmic rays traveling near the speed of light, and particles accelerated by violent events like supernova and black hole jets. Within the Milky Way, our solar system is protected by the sun's heliosphere, a vast bubble of charged particles and magnetic fields that deflect some of this radiation. Beyond that, the galaxy's own magnetic field provides partial shielding. But in the deep void between galaxies, there is no such protection. A ship and its passengers would be fully exposed to the raw radiation of the universe, a constant hail of invisible bullets tearing through matter, damaging DNA, and degrading electronics. To survive this, a spacecraft would need shielding of extraordinary thickness, perhaps meters of lead or water, or advanced materials we have yet to invent. But shielding itself adds mass, and more mass requires exponentially more energy to move. Thus, the very act of protecting against radiation makes the challenge of propulsion even harder. The cold of intergalactic space adds another layer of difficulty. While space is often thought of as simply cold, it is more accurate to say it is an environment where heat dissipates endlessly, radiating away until an object stabilizes just above absolute zero. In the void between galaxies, where even faint starlight is absent, temperatures sink perilously low, close to 2.7 Kelvin, the temperature of the cosmic microwave background, the faint afterglow of the Big Bang. Maintaining life in such conditions would require constant heating, powered by reliable and enduring energy sources. Machines, too, would need to withstand the brittleness and stresses that extreme cold imposes. Lubricants freeze, metals contract, and electronics behave unpredictably. On Earth, even our most advanced engineering struggles with extremes far less severe than this. And yet an intergalactic voyage would demand not just survival, but flawless operation across timescales longer than human civilization has existed. Then there is the question of navigation. Within our galaxy, spacecraft can orient themselves using the light of stars, pulsars, or other celestial landmarks. But in the dark between galaxies, light sources become so faint and distant that traditional navigation would fail. A traveler would be moving through a featureless expanse, where any small error in trajectory could mean missing the target galaxy entirely, drifting endlessly in the void with no chance of correction. This challenge is not just technical, it is existential. In a journey measured in millions of years, even the tiniest deviation at the start could compound into failure on a cosmic scale. Dark matter adds another unknown. Though invisible and elusive, dark matter makes up most of the mass of the universe, and its influence shapes the structure of galaxies and the spaces between them. In intergalactic space, Dark matter exists as filaments and halos, unseen but gravitationally powerful. We do not yet fully understand its distribution or its potential impact on travel. A ship venturing into this environment might encounter gravitational anomalies or tidal forces we cannot yet predict. The very nature of the medium through which we would travel remains a mystery. It is like planning an ocean voyage without knowing the currents, the depth, or the storms that might arise. And while emptiness and radiation are daunting, perhaps the greatest challenge of the intergalactic environment is time itself. Even if all other obstacles were overcome, the journey would take so long that survival becomes the most hostile factor of all. Machines wear down, systems degrade, entropy is relentless. The idea of a spacecraft functioning perfectly for millions of years stretches credibility. Every material corrodes, every circuit weakens, every system eventually fails. Life, too, is fragile. Radiation damages cells, isolation erodes mental resilience, and generations born in transit would live and die without ever seeing a destination. The intergalactic void is not simply space. It is time stretched into eternity, a gauntlet of endurance that no known organism or technology could likely endure. All of this paints a picture of an environment that is not merely difficult, but profoundly hostile to the idea of crossing it. It is not like crossing an ocean, where islands dot the way and resources can be gathered. It is not like scaling a mountain, where climbers can rest at base camps. The intergalactic medium is more like a perfect vacuum of hope, a place where every breath, every heartbeat, every watt of power must be brought along from the beginning. The void itself offers no mercy, no aid, and no shelter. It is the harshest possible environment for life and machine alike, and it stretches for millions upon millions of light years in every direction. For this reason, even if humanity achieves incredible feats of engineering, even if we solve propulsion, even if we learn to endure relativistic timescales, the intergalactic environment itself stands as a nearly insurmountable obstacle. It is not just distance or speed that defines why we may never leave the Milky Way. It is the nature of the void that lies beyond, a void so empty, so cold, so hostile, that it makes even the most advanced dreams falter against the reality of the cosmos. When we imagine the possibility of leaving the Milky Way, it is easy to focus on technology, on faster engines, stronger shields, and more resilient machines. But behind every spacecraft, every piece of metal or computer code, there are human beings. At the heart of this dream lies the question, can human life itself endure the demands of such a journey? The answer, when we look at biology, psychology, and the fundamental needs of our species, is sobering. The boundaries of human survival are not just defined by external challenges like radiation and gravity. They are also drawn by our own physiology and psychology, by the delicate balance that makes life possible on Earth. To step beyond the galaxy would mean stepping beyond that balance into an environment fundamentally hostile to everything that makes us human. Consider first the biological limits of our bodies. We evolved to live in a very narrow range of conditions: air pressure at sea level, temperatures that hover within survivable ranges, and the protection of Earth's magnetic field against cosmic radiation. Even in low Earth orbit, astronauts experience how fragile our biology is. The absence of gravity causes bone density loss, muscle atrophy, and shifts in body fluids that lead to vision problems. Radiation exposure increases cancer risks. The stress of confinement and isolation takes its toll on mental health. And these effects occur after just months or years in orbit. Now imagine extending those conditions for hundreds, thousands, or millions of years. The cumulative effects on human biology would be catastrophic without constant intervention. Entire generations might grow weaker, frailer, and less capable of enduring the stresses of such a voyage. Artificial environments, of course, could help. Spacecraft could simulate gravity through rotation, shield against radiation with dense materials, and provide controlled ecosystems for food and oxygen. But these solutions require enormous amounts of energy, maintenance, and precision. A single failure in life support systems could mean the end for everyone on board. On Earth, Ecosystems are resilient because they are vast and self-sustaining. In a spaceship, they would be tiny and fragile, dependent on human oversight and technological perfection. A closed-loop ecosystem that could endure for millions of years without failure is not only beyond our current abilities, but might be beyond the limits of possibility itself. The boundaries of survival extend beyond the physical into the psychological. Human beings are social creatures, shaped by contact with others, by culture, by the rhythms of day and night, by the experience of seasons, landscapes, and natural beauty. A journey outside the Milky Way would strip most of these away. Passengers would live their entire lives confined to metal corridors, artificial lighting, and synthetic food. For the first generation, this might be endured with the knowledge of a mission and a goal. But what about the 10th generation, the 100th, the 1000th? For those born into such a voyage, there would be no Earth to remember, no stars to see except through windows, no sense of destination within their lifetimes. Their entire existence would be defined by a journey they did not choose, and whose conclusion they would never witness. This raises profound questions about meaning and purpose in human life. Can generations live, work, and die for a destination that remains nothing more than an abstract promise? This psychological strain is magnified by isolation. On Earth, no community is ever truly cut off. Communication is nearly instantaneous across the globe. Even in our solar system, signals can be sent to spacecraft with manageable delays. But once we move beyond the galaxy, communication would become impossible. Signals take years to cross even the distances between stars, and for intergalactic scales, they would require millions of years. A crew traveling out of the Milky Way would not only leave Earth behind, they would leave behind the possibility of ever speaking to Earth again. They would be a civilization adrift, severed from their origins. The loneliness of such an existence is difficult to imagine. Beyond individual survival, there is the question of societal survival. Human communities thrive on trade, cultural exchange, and the interplay of diverse ideas and resources. A spacecraft would be a closed society, limited in size and diversity. Over generations, such a society could face stagnation, conflict, or collapse. Resource scarcity might spark competition, hierarchies could harden, and governance systems could falter under the strain of maintaining order across centuries. Unlike nations on Earth, a spacefaring community could not replenish itself with outside resources or ideas. It would have to maintain stability with what it carried from the very beginning, a task as daunting as any technological challenge. We must also consider reproduction and genetic survival. For a multi-generational journey, humans would need to reproduce in space, but the effects of long-term space travel on reproduction are largely unknown. Radiation damages DNA, increasing the risk of mutations. Microgravity may affect fetal development. Psychological strain could influence family structures and birth rates. To maintain genetic diversity, a large population would be required, but a large population requires more resources, more space, and more energy. The logistics of sustaining a thriving human community over cosmic timescales quickly spiral into near impossibility. Some have proposed storing frozen embryos or using artificial wombs, but these solutions only shift the challenges rather than eliminating them. They require perfect technological continuity over time spans longer than the entire history of human civilization. The boundaries of survival are not only about the ship or the journey, but also about what happens upon arrival. Suppose humanity somehow managed to reach another galaxy after millions of years. What would they find? Would there be habitable planets? Would resources exist to sustain human life? Or would the destination be just as barren and inhospitable as the journey itself? The truth is, there is no guarantee of another Earth. Habitable worlds may be vanishingly rare, and even if they exist, reaching one would be like finding a single grain of sand in an infinite desert. Survival would depend not only on crossing the void, but also on discovering an oasis at the end of it. A gamble so uncertain that it strains reason to consider. When we reflect on these challenges, it becomes clear that the boundaries of human survival are as confining as the physical limits of the universe itself. It is not only that the void is vast, cold, and hostile, it is that we ourselves are fragile, bounded by biology, psychology, society, and time. Our survival depends on an intricate web of conditions that exist only on Earth, nurtured by its air, its oceans, its seasons, its protective fields. To move beyond the galaxy is not just to travel far, is to attempt to carry Earth itself with us, in miniature, sustained without fail for longer than history has lasted. This is not a matter of building bigger rockets or stronger shields. It is a matter of confronting the very definition of what it means to be human, and whether that definition can survive outside the home that shaped it beyond the physics of light speed, the vastness of intergalactic space, the threat of cosmic radiation, and the boundaries of human biology. There lies a deeper and perhaps even more immovable barrier, the philosophical and existential limits of leaving the Milky Way. These limits are not written in the stars or encoded in the laws of physics, but instead, carved into the human mind, into our sense of meaning, purpose, and identity. Even if we could build machines capable of spanning galaxies, even if we could survive the cold and radiation, the question remains, why? What would compel us to abandon our galaxy, to chase a dream so far beyond the scale of our lives that it defies comprehension? The answer is not as simple as curiosity or survival. It reaches into the heart of what it means to exist as humans. Fragile beings who live not only in a physical universe, but also in one of values, hopes, and fears. At its core, the dream of leaving the Milky Way is bound to the ancient impulse of exploration. Throughout history, humans have looked to the horizon and wondered what lay beyond. From crossing oceans to exploring the poles to stepping onto the moon, the drive to go farther has always defined us. Yet, there is a profound difference between crossing a sea and crossing intergalactic space. The former promised land, resources, and new opportunities. The latter promises only the endless void. To leave the Milky Way is to chase a destination that might offer nothing more than emptiness. It is to risk everything for a horizon that will never draw nearer in the span of a human life. The philosophical weight of this difference cannot be ignored. Exploration has always been fueled by tangible hope. Without that, the dream becomes a hollow pursuit, an act of defiance against the universe rather than a continuation of human spirit. This leads us to the existential dilemma of purpose. A journey outside the galaxy would require not decades, not centuries, but millions of years. No individual or community, no nation could expect to see its completion. Generations would be born, live, and die within the confines of a ship, their lives defined by a mission they did not begin and whose end they would never witness. For them, the destination would not be real, only a story told by ancestors, a dream passed down like myth. The existential burden of such a life raises difficult questions. Can meaning truly be sustained across endless generations without tangible fulfillment? Would such a society find purpose in the journey itself? Or would despair, apathy, or rebellion corrode the mission over time? We are creatures who seek closure, who look for arcs in our stories and meaning in our actions. A voyage measured in millions of years denies that closure. It transforms human existence into an unending treadmill, where the act of moving becomes more important than the arrival. Whether humanity could adapt to such an existence is uncertain, and perhaps this uncertainty itself defines one of the great barriers to leaving the galaxy. There is also the question of identity. Humanity is inseparably tied to the Earth, and, by extension, to the Milky Way. Our myths, our religions, our philosophies, our art all are born from our experience of the night sky, of the sun and moon, of the stars that we can see. To leave the galaxy would mean severing that identity forever. No more constellations familiar to our ancestors. No more Milky Way arching across the night. No more Earth to return to. No blue oceans or green forests to inspire stories or dreams. In leaving, we would become something entirely new, no longer Earthlings, no longer a species of this galaxy, but wanderers in an abyss without home or heritage. Whether humans could psychologically endure such a loss of identity is uncertain. It might fracture us, leaving us untethered in ways that no technology could repair. This existential barrier also brings forth another profound question. Should we leave? Even if we could overcome the physical and biological challenges, is it desirable to abandon our galaxy? The Milky Way is not just a place, it is our inheritance, our cradle, and our future. It contains hundreds of billions of stars, countless planets, and mysteries that will take us eons to explore. Perhaps the pursuit of leaving is not only impractical, but misguided. Perhaps the true adventure lies not in fleeing the galaxy, but in embracing it, in uncovering its secrets, and making it our eternal home. The philosophical limit here is the recognition that leaving may not represent progress, but rather a misdirection of effort and purpose. It forces us to confront whether expansion is always the same as growth, and whether chasing the unreachable distracts us from the wonders within reach. Another layer of the existential limit comes from the inevitability of cosmic finitude. The universe itself has a destiny, a heat death, a collapse, or some other fate dictated by physics. No matter how far we travel, no matter how many galaxies we attempt to reach, the end is already written in the laws of thermodynamics. Energy will dissipate, stars will die, and the cosmos will grow cold and dark. Against this backdrop, leaving the Milky Way does not guarantee survival or immortality. It simply delays the inevitable. This realization forces us to ask what survival really means. Is it about extending our timeline by a few million or billion years, or is it about making meaning in the time we already have? If the universe itself has limits, then so too must our ambitions. Chasing eternal expansion might be not only futile, but also philosophically empty, a denial of the impermanence that defines existence itself. And yet, within these existential limits, there is a kind of paradoxical beauty. The impossibility of leaving the Milky Way does not diminish us. Instead, it situates us within a larger truth about the universe. We are not masters of the cosmos, but participants in its grand design. The boundaries set by physics and philosophy remind us that meaning is not found only in conquering distance, but also in understanding and embracing our place. To look at the stars and know we cannot reach them does not make them less beautiful. It makes our vision of them even more profound, because it is paired with humility. The universe is vast, and we are small. And perhaps in that relationship lies the deepest truth of all. For humans, the challenge of leaving the Milky Way is not just about engineering, but about confronting these existential questions honestly. Do we define ourselves by how far we travel, or by how deeply we understand? Do we measure success in distances crossed, or in the wisdom gained from accepting limits? The philosophical and existential barriers to leaving the galaxy may be the most immovable of all, not because they forbid us from trying, but because they reveal that the journey itself may not align with who we are or what we seek as a species. They remind us that, in the end, the cosmos is not only a space to be crossed, but also a mirror in which we see ourselves, our hopes, our fears, and the meaning we assign to existence itself. As we have journeyed through this exploration of why humanity will likely never leave the Milky Way, the reasons unfold layer by layer, each one more formidable than the last. The first challenge lies in scale. The distances between stars, let alone galaxies, are so immense that even light itself takes millions of years to traverse them. To go beyond our galaxy is to step into a realm where distance becomes almost meaningless in human terms. Then comes the law of physics itself, Einstein's barrier of light speed, a cosmic speed limit that no ingenuity has yet shown a way to bypass. Even if we imagine a civilization capable of approaching those speeds, the universe itself adds another wall, the expansion of space. Galaxies are not simply far away. They are being carried away faster than we could ever chase them, receding beyond an event horizon we can never cross. Beyond this lies the void, a hostile intergalactic environment filled with emptiness, radiation, and cold, where no resources exist to sustain life or machines for the eternity such a voyage would demand. And even if somehow a vessel could survive such a journey, the fragile boundaries of human survival, our biology, our psychology, our social needs are stretched to their breaking points. But perhaps the deepest barriers are not physical at all. They are philosophical and existential. To leave the Milky Way is not only to confront the limits of technology, but also to confront the limits of meaning. Can generations live and die for a destination they will never see? Can a species untether itself from the identity born of Earth and the stars of this galaxy? And even if we could, should we? For within the Milky Way lies an abundance of wonders yet unexplored, billions of stars, trillions of planets, mysteries that could occupy us for as long as we endure. In this light, the impossibility of leaving the Milky Way does not appear as a failure, but as a reminder. We are bound not by weakness, but by the universe itself. And within those bounds, we are offered a home vast enough to inspire endless curiosity and meaning. The dream of other galaxies may forever remain just beyond our reach, but the story of humanity will always be written under the arc of the Milky Way, our eternal island in the sea of the cosmos.